but I don't have one. Okay, let's do this. Okay. Okay, actually, let me go back to my scratch buffer. I want to show it to you here. Here's the key. When we start off, we can look at node 1, and we'll call it, say, current. And then, as y'all said, we need to remember what's going to happen with node 2. And the reason we need to remember both of them is that we're about to disconnect them. We disconnect them, and we make this pointer point the other way. Like that. Because that's going to be a tail, so it has to point to none, right? But now they're disconnected, so they'll get lost if we don't remember what new is. So that's our 2 pointers. But here's the key, which is we're about to disconnect node 2 and node 3. So if we don't remember those as we are, we're about to move this pointer over here. So we already have to remember node 1 and node 2, but we better, on our next, as soon as we leave the head, we should remember 3, because otherwise we will forget one thing as we are connecting. It's like, I think of it like connecting boxcars on a train. So we're going to disconnect those 2 and then reconnect these 2, but in the opposite direction. So there's the thing. We have to have 3 pointers. Otherwise, when we disconnect these nodes, we're going to lose track of something. And after we've connected them, we can now move all of these down. We can move this down here, because now we have to keep track of these 3 nodes. There. Since, again, we've already disconnected these 2, so we better remember them. And we're about to disconnect these 2, so we'd better remember them. Otherwise, we will wind up with 2 halves of a linked list, and we won't know, where they are. We'll lose half of our linked list, as it were. So we would disconnect those. And of course, that really happens in 1 step, not in 2 steps like I'm doing it here. We just say node 3 next, you point to node 2. And once we're done with that, we can move our pointers down. Does that make sense so far? Anyone pipe up if it doesn't? And we'll keep on doing that. I'll move, we redirect node 4's next pointer until we get to the end. We redirect node 5's pointer. And then when our new is, now our new is out there in no man's land, it points to none. So that's fine. We still have to redirect this pointer to here. And now we're done. When new is none, because it's gone 1 step too far, we know that we are done. And we probably want to, make our self.head be node 6 and make our self.tail be node 1, but otherwise we are done. That's how that works. So to reiterate, when we start out, we can just have like a current and a new. But after that, we're going to need 3 pointers as we move along. I will pause for any questions. Well, I will let you think of questions while I go over here and code it up real quick. So let's do def reverse SLL, self, and let's see. We can make current be self.head, and new can be current.next, aka self.head.next, same deal. And then we're going to make our, what I want to do, I want to make self.head current.next can be none, right? So I redirect that pointer, I point it around because it's going to be a tail. Now, as long as we've got new, while new is not none, we could also just write that as while new, because none is false. But I'm going to say while new is not none to make it more explicit. while new is not none. We're going to bump these all along and then change the pointer. So previous, if we had a previous, because we're gonna, equals current. Current, you can equal new. New, you equal current.next. So we bump them all along. And now we say current.next equals previous. So we change that pointer, yank it around to point the opposite direction. And that's it. That's all we need to do.
Wow.
We'll go around again. You know, new is now the next one, and so forth until it becomes none. And then when it's none, well, we redirect our pointer one more time. We come up here, we say, aha, we're at the end of the list. We have reversed our list. We can then do, so we didn't change our self.head and self.tail. Don't really have to, you know, I guess, why not? There's actually a little syntax in Python. It goes like this: self.head, self.tail equals self.tail, self.head. That's kind of fun. And then we're done. We don't have to do anything else. If we had more time, I would code up a little function to print out everything in the list, so we could, you know, print it before and after and see that all the values are different. But I don't have time to do that. Pause for questions on that. Cool. All right. Let us, well, that was fun, I think. We're going to go Slack. We'll play that later. Let's do Q. We're going to do this like pretty quick. Was anyone, well, I don't want to put it like that. How did everyone do with Q, I guess? I should do a poly here. Were you able to implement a queue using a linked list? It's a binary answer, yes, no. 1, 0, I make it anonymous, I send to channel. Okay, that is good to know. I will go ahead and code this up then. So let's go do that. Go back up, I go into the queue, go into the queue folder, open queue.py, and here we are. Right. So I won't review the logic for why we want to use a linked list to implement a queue. But if we ask ourselves, what can we on-queue and dequeue from with constant time, we can probably see that a linked list is going to be better than an array for this. So we want to import our linked list and use it here. Python's, I just like the way Python does imports from other areas. JavaScript is much easier. In Python, you have to import sys, and then we do like sys.path .append, and then we can go up one level, we can go into doubly linked list, and now that folder is where Python knows to look for it. So I find that annoying, but there it is. And then we import from doubly linked list, we import doubly linked list. Now we have doubly linked list where we can use it as usual. So let's see. So our storage will then be a doubly linked list. Like that. And notice we're keeping track of our size as we go. So that's that. What should I use? So of all the methods in doubly linked list, what should I use to onQ? So let's see. So onQ, you come in at the back. So what might I do to add something at the back of our doubly linked list?
I guess just go grab your add to tail code, right?
Yeah, that's what I would do. Let's do self.storage.add to tail. So it's at the back, the item. Done. Pretty easy. And then we want to remember to increment our size because we are keeping track of that. Self.size equals 1. How about DQ? So DQ at the front.
We have our add to head. Oh, DQ.
DQ. Yeah, you're thinking the right. I can tell you're on the right track. Self.storage dot remove from head. There we go. And yeah, and actually, remove from head, if we go and look at it, will give us back what we took out. And we probably want to do that here as well, so we return that. And let's decrement our size, like that. Now, I think if we go and we look, I'm going to split my buffer, go over the other side, go back to our doubly linked list. Where am I? Here we are. If I go and look at remove from head, it will call, now that we've refactored it, it calls self.delete and returns the return value. So, if there's nothing there, if there's no self.head.value, it's just going to return none, which is fine. But if there is nothing there, we'll probably size, or we'll wind up with negative numbers. So let's do like if size is greater than 0, we'll decrement size. And in any case, we'll return whatever remove from head gives us. And finally, the length, we can just return self.size. And we're done. That's our Q.
Size.
It is, isn't it?
Yeah.
Python can be very pleasing in that way. And again, this is, I guess, kind of to sort of drive home that, again, the linked list is, is what we care most about a linked list is how it lives on the computer, all these pointers and values. But the Q is kind of, it's like an idea. We went onQ and DQ. So we could do this, anything, we could do this in, maybe several ways. As long as we have an onQ and DQ, we have a Q. OnQ and DQ with O of 1. I want to say in one of the modules, I think in graphs, they make a Q class where they make an onQ and DQ, but then they use like an array because they didn't want to go to the trouble of doing it the right way. And they were like, yeah, but it's fine because we don't have that much data. It's not really going to be much of a hit. So they wrap their abstract, the sort of data class around something else. I don't know. Just to emphasize that it's sort of one level above is abstract. Okay, cool. I will pause real briefly for that. And then I want to move on to our final project of the evening. Okay, let's talk about buffers. So we're all staring right now at my text editor. And you may have heard the word buffer, a text buffer. All of our text editors have text buffers. In a buffer means it's something where you store things temporarily. It's like why videos, when they're slow. Someone said line 15 should be self.size. Aha, thank you for that. Line 15 should indeed be self.size. There we are. Yeah. A buffer, if you're like buffering a video, it is storing the stuff that's streaming in sort of temporarily so that it can then run it all nice and quick for us to watch. So that buffer is a temporary storage area. Similarly, when we type into our text editors, there's a temporary storage area for the letters that we type in. Because eventually, our text editors will save that to a file. And I could say more about that, but that's a little bit of computer architecture type stuff, and I don't want to get too off track. So let me switch to my Scratch buffer, for instance. So here is my empty buffer. I just sort of throw away buffer. So what I want us to think about is when we are typing on the page, like I type hello world, that text has to be stored in some kind of data structure. It has to live somewhere, right? So I want us to think about what kind of data structure might we use. But maybe before we do that, let's think about what operations we want. So if I am adding a letter, what do I need to do on this data structure, whatever it is? Clearly we know it's probably going to be one of the ones we've looked at so far. So it could be a stack, it could be an array, it could be a queue, it could be a linked list, single linked list even. It could be a double linked list. But in any case, what am I doing when I go to the end of my line here? So let's say this line holds a data structure. And I'm going to go here, and I'm going to add, it's an A. I add an A. Or an S. I've hit my caps lock here. What operation do I need to do? Yeah, we could call it insert. Totally.
Array, then we can say that it's append.
Yeah, it's like an append. I think between append and insert, I like both of those. I'll go for append to emphasize that we're adding at the end of our data structure. Add to, let's see, end/right here. Right, so this at the right side here. What else might we want to do? So let's say that's one thing. What if I start deleting stuff? Might want to do that. I'll just call that remove from the end. So there's the second thing we might want to do. I'm going to make these bullet points. Operations we want to support in our text buffer. So I'm going to, obviously, like our editors are very complicated. They do lots of things for us, and we're not going to do all the rest of that. We're going to do something very, very simple. We'll consider, like a single line, and we want to add text to it. ... What else might we want to do with this single line of text? We're going to have a data structure that represents this single line. So I started to say remove from end, aka right side of data structure. And also, raise a hand to ask a question if this is sort of confusing for you. Well, I will suggest to you another thing we might want to do. What if I go to the beginning of this sentence and I start typing stuff here? Or I go all the way to the beginning, I insert something here, like an exclamation point. We might want to, we could call it prepend, copy and paste. That's a great one. prepend add to front slash left of our data structure. Remove from end, and then of course we would also have remove from front slash left side. And then we had copy and paste suggested, which I think is a great suggestion. Let's think about, so with copy and paste, what we're saying here is if I had, suppose I have a line here and it's got 80, 80, 80, 80. And I have a line down here. It's like that. I want to be able to take that line and then go to here and paste it. So there were two data structures that we have joined together. It's kind of like appending a whole bunch of text at a time. Really, it's like when I have one data structure, whatever it is, I'm going to join it with the next one. Or I could like backspace. In any case, however we get it there, we want to join these two data structures together. Because again, this is like one data structure here is one line I'm typing on. And there's another data structure down here, it's another line I'm typing on. And we're going to join those two data structures together. So I will call copy and paste join. Yeah, so copy and paste is kind of like concat here. It's kind of like concatenating two data structures together, slam them together to make one. I think that is probably a good start for us. I will add one more, maybe we'll have time to do this, maybe we won't. We'll call it like string. Stir for string. And the point of that one is, like, suppose I'm not saying we should, suppose we use an array, then every one of these letters is going to be like a separate thing in the array. And we want a way to get them out in a way that we can print them using Python and see what's in it. So we should go down the line and add them up into a big string. So that's a convenience function, so that we can print out what is on our line and check that we're doing it right. Questions on that? Real quick. Does that make sense, or is anybody confused?
What str will do? Last one.
Yeah, totally. That will, so suppose we decided to use a stack for our data structure. Then this entire line would be stored in our stack, or I should say, I'll say an array. Suppose we decide to use an array. And so every line here, every letter on our line is stored in our data structure one at a time like this, until we get down to the end where we have this weird KJ thing because I was typing random stuff. And we would like to print all of that. So string is going to help us print it. Basically, it'll look like our string to return is an empty string, and then we're going to iterate down, for care in our data storage, string to return plus equals at care. So it'll build a big string. So then we can print it, print our string to return. Does that make sense? So our function string is going to do these lines here. It's going to build us a string that we can print out of our data structure. Okay. Right. Let me delete some of this weird stuff here. So let me reiterate. Our mission build a data structure to hold text we type in. Kind of on a line, but we also know that we want to join things together. So it's kind of like copy and paste. And our data structure choices, our tools at hand, are these ones here. Yeah, those ones there. And our supported operations are down here. We want to do all of this. So given that, how can we choose which data structure to use? I think we should consider how long these operations will take in each choice. For instance, if we're adding to the end and I'll say an array. Let's do array first. We all know that adding to the end of an array, pushing, is O of 1. That's constant time. That's pretty quick. But prepend is O of n. So that's not so quick. The same thing applies for removing from the end, it's O of 1, and remove from front. It's O of n for an array. Joining data structures. That might take a little bit of time. Let me think about that, actually. That means we would have two arrays, you know, which have like, yeah?
I'm deleting a good runtime when we are in the linked list, because it will be O1 all the time if we are inserting anything or deleting anything.
Yeah, yeah, awesome. Let me say that, I'll say that again, as you said. So we saw that at least a couple of these operations were O of n with an array. If we considered a runtime with a linked list, say a doubly linked list, then both the append is still O of 1, but prepend is also O of 1. Removing from the end is O of 1. Removing from the front is also O of 1. And joining data structures, so we have like two linked lists we want to join together. Some of you may already have a sense that won't be too hard. We just have to point the pointers in the right direction, and we'll be good to go with that. So let's go ahead and use a doubly linked list for our text buffer. So with that said, let's go ahead and do that. And in the interest of time, I'm just going to open in this same folder with our doubly linked list. I will open text buffer.py. What's it? Python, I think that is there. So we want to implement all of that, like that. So let's do that. We'll do a class text buffer, and we need our def init. So it takes a self. Forgetting it takes a self now. We also want to, it's from the linked list, import the linked list. And we will do, say, self.contents, contents of our text buffer is going to be a doubly linked list, right? Easy peasy. Let's do append. How should I do append? I'm going to add to the end. What should I use for that?
Add to tail.
Yeah. Self.contents.add to tail. And actually this method should take something. Maybe it takes a character. And we'll add that to the tail. Like that. That's pretty easy. How about prepend? think I'm not going to make y'all say that. I think we maybe guess it's going to be add. Yeah. Not tail. Boom. Okay. We're moving right along here. Delete from the end. We're going to loop around and make this a little bit more elaborate, but not a lot.
Remove from tail.
Yeah. Let's see, let's do remove from end. We'll say self.contents.remove from tail. And the same thing for the head. Remove from the front. We remove from head. Okay, not too bad. Let's think about how to make this a little more interesting. Well, actually, first, I guess we should go ahead and do join and string. So let's do join. So we'll do def join data, join text buffers. It's going to have self, and it's going to take a buffer. So this buffer is just another text buffer, right? So how can we join them together? Anyone have any ideas?
Self.content.tail equals the head of the buffer.
Yeah, sorry, say that one more time.
Content.tail will be equal the head of the buffer.
Yeah. Let me think about it. I'm trying to think if we're going to run into any problems with that. I had a slightly different method in mind, but I'm not saying this won't work. I have to think about it. Yeah, that's right. Self.contents.tail.next, I guess. So we'll take our tail and we'll make it point to the other buffer's head. I guess the other buffer.contents.head. Because it's a text buffer. Right? And what else? What else should we do?
I'm confused here.
Mm-hmm.
I'm confused here. So why this buffer, how it looks like, don't we need to describe it first? Like what it will take in a buffer class? Like what it should be? It should have a tail or a head, or what it should have values?
Let me.
Like that.
How can we? I'm sorry.
How can we take it like that? That it will be having a head.
Oh, I see what you're saying. Yeah, actually, I think you're right. Like we probably, like if I make out, maybe I should leave a comment. We should like really check that this buffer we're getting, is an identical text buffer, right? It should also have up on like line 15. It should be have contents of a doubly linked list. Is that what you mean?
Yes.
Yeah. So right now we're making a big assumption that when we try to join these, the other one looks just like this.
Yep.
And we probably should not make that assumption. For the purposes of this exercise, we'll do that, but text buffer. But you're absolutely right. We should check that. So I don't know. Leave a to do. You're allowed to leave unfinished code if you write a to do and feel bad about it. I don't make the rules. I just live by them. Okay. What else should we do? Yeah, we could use is instance. Yeah, very good. Yeah, right. So now we've made our tail point to the next one. We should make this tail, the self.tail equals other buffer. I should say self.contents.tail. .contents.tail. So now our tail is the same as their tail. What else? What about the other buffer's head? What should we do with that?
Self that contains that head equal to the self that contains.
Yeah, yeah, their head, the other buffer head, their head, the other buffer's head should come be this one's head. Like that. So we join them together as easily as making our tail point to their head. And then we make our tail identical to their tail. And we make the other buffer's head equal to this buffer's head. And then we have pretty much joined them together. Actually, no, wait, I'm forgetting one thing. We made our tail point to their head. But we didn't make, this is a doubly linked list. So their head.
Are we taking care of the case that number one text is again, I mean, vice versa the case? Are we taking care? Because that can be also copy and pasted, and the other one also get copy and pasted.
Oh, I think I see what you mean.
So suppose.
I think I see what you mean.
Yeah, ABCD is there, one text, and the other text. Yeah. So are we going to take both vice versa, like both can be added next to
Yeah, we're adding it to the end.
Yeah, so what if we paste at the front like that?
Yeah, right.
Then we want to do the other way.
Oh my God, it's
so So maybe I should really like rename this. I should name this, you know, join other text buffer to end or something like that. Join text buffer to end, because that's what this handles. But what about joining text buffer to the front? We could totally do that as well. Oh yeah, before I forget, what else can we? Yeah, what about join text buffer in the middle? Other buffer.contents.head dot previous equals self.contents.tail. This is because we're assuming they're both double linked lists. We have to make the other one point the other way. Just what I thought of that. Great. That should be correct for join text buffer to end. But as you will say, what about, you know, yeah, join text buffer to front. Join text buffer. I don't know. Dump it in the middle. Put text buffer in the middle. There's a true insert for you. I think Layla suggested earlier. Yeah. What if we want to? So let's not do that for now. But those are totally good suggestions. We could do front in a minute, but maybe I'm running out of time, I'm afraid. Remove from end. What if I want to, let me jump back over to my left side here. What if I want to like highlight, I'm highlighting, and I want to delete, you know, 5 characters like that. Can I make remove from end do that for me? How could I do that? Say I'm going to highlight, you know, say, okay, 5 characters. 4 characters, you're going to delete that. Can I refactor this a little bit so it will do that for me?
We'll just call it X times.
Yeah.
Well, and
Yeah. So let's say, you know, number chars to remove and for X in range, number of characters to remove, self-constant remove from tail. And obviously the same thing for that one. And cool. So clearly we could keep on going and going. Like for the init, we could make this take, what if I want to, so I have, say, a bunch of text here, and I'm going to go down to an empty spot here, and I create my text buffer by putting it all in at once. So our init needs to take a string. So it'd be like starter string, and we'll set it to none by default. But if we do give it one, we could just do if starter string for char in starter string. I think I can just iterate across the string this way in Python. Self dot, let's see, we'll do append, right? I think that's correct. Self dot append char. So you can init with a string if you want.
self.content.
Oh, thank you. It's self.contents. Dot append. Yeah. Otherwise, it's going to throw an error very quickly. So there's the basic idea. And I love that y'all are problematizing this. You're already adding many more things that we could go and do. If only we had time. And if we really, really wanted to like write our own text editor, we could totally do that. But sadly, we don't. Nevertheless, there's sort of the idea. I could show you as well, I guess. Do I want to do this? Yeah, I'll do it. I'm going to split my buffer on this side. I'm going to open the directory view in my editor here. So here's all the files that we've created in this. So one interesting thing is that when any program needs to write a file, it actually has to ask the operating system, can I write this? Actually, it asks the operating system to do it for it. Like a server calling a client. Like a client calling a server, I'm sorry. That way the operating system can check, do you have permission to do this? Like we have to do sudo sometimes on the command line. We give ourselves extra permissions. Your program may or may not have permission to do that. So when we type in a buffer, as I say, it's a temporary holding spot that your editor is using. It has not written to a file yet. It doesn't want to write to a file yet because it would have to ask for permission. And so it creates a temporary buffer, a temporary file, and holds this text, in some sort of data structure. I don't know, maybe it actually uses a doubly linked list. In my editor, you can actually see that it creates this weird temporary file that has not been written to my computer. It's like if I edit this, oh, look at that. It creates this weird sort of fake file to tell me that it's done something, but it has not yet been saved. Now, if I save this file, it disappears. Because then my editor said, okay, you want me to save that? Okay, I'll take what I stored in my data structure, and I'll send it to the operating system and say, please write this. So please save it. And it does. I could say more about that, but that's not really the point. The point is this data structure that we have now figured out how to use as a text buffer. I really need to let y'all go. Guess we didn't do string, but I think I will let y'all figure out how to iterate down and add to a string, return the string. I think you can do that. Okay, we're a few minutes over time. Let me check Slack. Questions? Any final questions before we go? I believe the next challenge, the next thing y'all get to do is to go implement a least recently used cache. I think the next thing up, depending where you are in the project. Will the challenges be a new thing? How do you mean? Jesse, could you elaborate on that for me a little bit? I believe the challenges are really more are all contained in that same project. So when I say challenge, I just mean the next data structure to do. So yeah, they say to go through all of them. So do queues, do doubly linked lists. We did that together. I want to say we're going to do binary search trees next week. So I think next up is, if you've done, we've done queue, we've already have a doubly linked list. You get to do a least recently used cache, I believe. Oh, the breakout room challenges. They could be. Would you like more of those? I'll see if I can come up with more.
Yes.
Because that was fun. All right. Okay, I've kept you 10 minutes past. Thank you all so much. This was a lot of fun. Best of luck on your LRU cache. Have a good night.